Hey guys, Mr. Janowski here. This is part 4 of the chapter 35 slides. So in the last one, we learned how to start to analyze circuits, and we learned about shorts and opens and things like that. So we're going to keep going, getting more and more sophisticated with this stuff. And in this part, we're going to learn Kirchhoff's laws. So to review, what is the equivalent resistance of a short circuit? The equivalent resistance of a short circuit is 0 ohms. In this circuit here, this last guy here makes it a short. So you may have been trying to put all these resistors in series, but by having this guy here, no current's going to flow through any of these guys. It's all going to go this way. And it's a path of no resistance. So there's the equivalent resistance is 0 ohms. And what is the equivalent resistance of an open circuit? That is infinite ohms. So depending on what you're trying to do here, maybe you wanted these guys in parallel and then that in series going back to here. But yeah, by having it open, essentially you've got an infinite resistor here. So I said parallel. Imagine these were supposed to be in series. Whatever. The equivalent resistance of an open circuit is infinite. So how is analyzing a circuit like doing a Sudoku? So it's a lot like doing a Sudoku because you're going to start off with a certain number of clues, and then using those clues, you figure out new clues. And then you take those new clues and you figure out still more clues. And you just keep doing that over and over again until you're done. And just like Sudoku, there isn't necessarily one correct way of getting to the final answer. There is one correct final answer. No matter how you do it, if you do it right, you should end up with the same answers for everything. You can take a certain number of clues and combine them in different ways. Like a Sudoku. Kind of rambling here, but I think you get the idea. I hope you get the idea. If you get confused, watch these videos and the other video that I have about analyzing a circuit from the study guide. So here is Gustav Kirchhoff. So he came up with two laws that are very useful in analyzing circuits. We call them Kirchhoff's laws. There is KCL, Kirchhoff's current law, and KVL, Kirchhoff's voltage law. And other physics teachers might call them rules instead of laws. I guess probably they're closer to rules, but these abbreviate nicer. KCL is a nicer acronym than KCR, but whatever. We're going with KCL, KVL. So the first one, KCL, the current law, it follows from the law of conservation of charge. If you have charge moving into one place, charge is neither created or destroyed, which means all of that charge needs to go out of that place. So two ways of stating that. The algebraic sum of currents in a network of conductors meeting at a point is 0. So I don't actually like that way of thinking of it. I like this way. This is the more plain English way. The total current flowing into a junction must equal the total current flowing out of that junction. That's more useful to me. So the voltage law. The directed sum of voltages around any closed loop is 0. Again, I don't like that way. I like the other way. The total voltage gains and drops around a closed loop must equal 0. So the second way, this is the idea we're going to use to actually do problems. So KCL and KVL are very useful when you're analyzing circuits. So if you started with this guy, what you would do is first start simplifying things, realize that these two guys are in parallel, so find the equivalent resistance of those. Then that equivalent resistance is in series with this guy, so you find the equivalent resistance of this combination, and you're down to here. So again, when you're doing this, don't be lazy. A lot of you have been trying to be lazy when you're doing this. Make the intermediate circuits. Don't try to do all of the small math all together in one step. It's too easy to goof, and it's impossible for me to see what your thinking is if you didn't write it down. So make the intermediate circuits. It also turns out that it's very useful to have these guys when you're going back through the problems to figure it out. The intermediate circuits, that's where you find your clues. So if we're looking at this, first I guess we'll look at KCL. So we simplified this guy to here and then to here, and then it's just Ohm's law to figure out the current leaving this guy. So you're going to have a current of 0.3 amps leaving the battery, coming up to here, and then what happens here? It splits. So you're going to have I1 going this way through R1 and I2 coming down this way. And then at the other point, at this junction here, at B, you have I1 and I2 combining again back, and they're forming I1. And if you want, you can also give it a nickname, call it I3, because it's going to go through resistor 3. So the algebraic sum idea, you can think of it this way and kind of write it mathematically this way, which is if you add up all of the currents coming together at a point, they have to equal 0. So you had you had I coming in. So in this formula here, that's a plus. The plus is implied. I, and then you have I1 going out, so that's a negative, and I2 going out, so that's a negative. And put them all together on the left side, and they must equal 0. You can think of it that way. I prefer to think of it this way. It is exactly equivalent. This just makes more sense to me. The total current flowing into a junction must equal the total current flowing out of that junction. So the total currents flowing in your math, that ends up on the left side. The total currents flowing out, they all end up on the right side. So I coming in becomes I1 and I2 going out. So what would KCL say about junction B? What would the math look like? At junction B, you have I1 and I2 coming in. Here's both ways of looking at it. You have I1 and I2 coming in, so those are pluses, and then you have I going out, so that would be a minus. But again, the clearer, more useful way of thinking of this is you have I1 and I2 coming in, so they're positive on the left side, and then you have I going out, so that's positive on the right side. So to do KVL, when you're looking at this, we're going to look at two different loops here. We're going to look at the blue loop, which starts at A, and then we're going to look at the green loop, which starts at W. So for our blue loop, we're going to start at A, and we're going to follow this all the way around. So this is where we get our laws for gains and drops going on here. So again, I always like to start at the bottom left corner and then go clockwise. Doesn't really matter how you go, but I think it's a good idea to pick one way and always do it that way. So starting here, going from A to B, this is going to be a gain because we're going to go through a battery from the negative terminal to the positive, so that makes it a gain. Then going from B to C, well, that's just wire, so nothing happens. From C to D, that's just wire, nothing happens. And then we're going to go from D to E. So going from D to E, we're going with the current through a resistor, so that's going to be a drop. So at that point, we would call this minus V2, being the voltage across resistor 2. Then you go E to F and F to G. Those are just wires. Nothing happens there. And then you get to the third resistor. So going from here, G to H, we're going through a resistor. We're going with the current, so that's going to be a drop. So that gives us this minus V3. And then we go from H back to A. So we end up with this formula, V minus V2 minus V3 equals 0. Now doing the green loop. Start at the lower left and then go clockwise. So going from W to X, nothing happens. We're just going along this wire. Nothing's happening there. And then we're going to go to R1. So going from X to Y, we're going with the current. So this is going to be a drop. If you go through a resistor with the current, you have a drop. Y to Z, nothing happens. That's just wire. And then going from Z back to W, we're going against the current through a resistor. So that ends up being a gain. So the formula we get from that loop ends up being minus V1 plus V2 equals 0. So to review, what is a short circuit and what is our equivalent of a short circuit? A short circuit is when you have an unintended path with no resistance, and the equivalent resistance of that is going to be 0. So what is an open and what is REQ of an open? An open is when you haven't actually completed the circuit. There's no complete path for the current to flow through, and the equivalent resistance in that case is infinity. So what is Kirchhoff's current law, KCL? A couple ways of thinking about it. The most useful way to me is the total current flowing into a junction must equal the total current flowing out of that junction. And then what is KVL, Kirchhoff's voltage law? That is the idea that around any closed loop, the total gains plus the total drops must equal 0. So that's it. Hope that helps.